Hello everyone, Anirudh here. I'm a Chennaiite and currently a third year undergraduate in the Department of Computer Science and Engineering at Indian Institute of Technology, Kharagpur. Right? And Kharagpur is in West Bengal for all those who do not know geography. Right. And today I'm actually very honored to be taking chapter Nuclei, that's chapter 13 of class 12 physics. And I'll be doing some exercises while providing a brief of the chapter. Right. First of all, first thing on our docket today, the chapter itself, right? Nuclei is a major part of nuclear physics, right? One of I think the four major chapters in modern physics in class 12 physics, right? In this chapter, before this, you'll be reading about the dual nature of light. You'll be reading about how light behaves as a wave, how light behaves as a particle, and what the quantum nature of light really is, right? Why is light? Why does light behave that way? Why does light have momentum? Why does light have energy in it? Right? You read about the quantum nature of light. Then you proceed on to your atoms, your molecules, the building blocks of day-to-day life, right? You learn about what they are, how they interact with the world around us, and why exactly is the macroscopic world so different from a microscopic world? Why exactly are there so many different phenomena that take place in the microscope that we cannot see in the macroscopic world? Why exactly does quantum, why exactly, there are quantum effects, right? In this chapter, you learn more about the center of each of those atoms, because an atom is mostly space, right? Everybody, you would have learned in a previous chapter that the electrons surround the atom in a shell of around of a radius of 10 power minus 10 meters. Well, the nucleus itself has a radius of 10 power minus 15 meters, right? The 5 orders of magnitude of 10 that is in between the first shell of electrons and the nucleus itself, that's empty space, right? So what exactly is this nucleus and why is it important? That's what we're going to learn in this chapter, right? So first of all, we have this introduction. We have the atomic masses, we have the composition of nucleus, right? Where they talk about the different composite particles that make up a nucleus. That are the protons, neutrons, right? And if you, if you're going to study more in depth about protons and neutrons, you'll notice that they are made up of quarks, which come in 6 flavors or 6 types, right? You don't call them types, call them flavors, but I digress, right? It's not really important, but that's just something, right? And since they are actual matter and they are not really energy aberrations, they also have mass, right? And how you define this mass is by this unit 1U, right? This U comes from, you would have learned in 11th chemistry that this U is the second unit. The first was atomic mass unit, that is AMU, which then later came to be defined as a unified unit because you had atoms, you had molecules, and you had some other things that came up and confused the shit out of everyone. Right. So everyone decided to use just U, the unified mass unit, to simplify matters a lot. Right. And cement has quantified the mass of C12 isotope. And that's 1.992647 in 10 power minus 26 kgs. They did this using a very sensitive balance. I think it's a gram balance, right? And you find out the value of 1U, the conversion from a unified mass unit to the kilogram, right? Then you see that you start representing various elements, the atomic mass of various elements using this unified unit. And you see that there are some there are some deviations from whole numbers, right? And then there is this paragraph about how you how you represent the mass number of some element that has many isotopes, which are not which do not have a negligible distribution, right? For example, chlorine has 2 isotopes, 35 and 37. And they are relatively abundant in 35.4 and 24.6% respectively. And you take the weighted average to get the final mass number, that's 35.40, right? And that's kind of the atomic mass of chlorine, which if you see a periodic table, you usually see represented as 35.5. Right? And then you have the fact that a lightest element, hydrogen, has 3 isotopes, hydrogen, deuterium, tritium, and tritium is radioactive. Everybody should know that. Right? The nucleus of the lightest atom has, is usually called the mass of the proton because the mass of the electron is pretty negligible, right? And the mass of the proton is 1.00727. Do not forget this value, right? That is a mass of, how to say this? This is the mass of a free proton, right? A proton that's not inside a nucleus, a proton that's not attached to any neutron, a proton that does not have an electron surrounding it. This is the mass of a free proton, right? That's 1.00727, right? But usually what you do is you take the mass of the hydrogen atom as the mass of the proton, because the mass of a single electron is 0.00055 U, right? That's 5.5 to 10 power minus 4 unified mass units. And that's pretty negligible, right? Nobody cares about it. So basically what you do is, you know the mass of the hydrogen atom pretty perfectly. That's 1.007825 or 783 U. Depends on how many significant digits you want to represent it by, right? And that you just basically say that this is the mass of the proton, because this is very minimal error, right? So nobody cares, right? And then finally you come to the fact that a positive charge in the nucleus is out of the protons. Then you get the fact that the atom is neutral, charge of the nucleus is plus ZE if the charge of atomic electron is minus ZE. Because the number of electrons is easily countable, they are situated in a wider shell, right? And the nucleus is pretty close. It's pretty small also. So you can't really guess the charge of the nucleus unless it's by some kind of an electroscopic measurement, right? And then comes the discovery of neutron by James Chadwick, right, where he did the radioactivity experiment and found that there are particles which are not exactly light, because if that's light, the energy of photons has to be much higher than available for the bombardment of beryllium nuclei with alpha particles, right? So this radiation, he found that it's of other particles called neutrons. And he found from the mass of conservation of energy and momentum that the mass of a neutron is 1.008665 units, right? And finally, you come to the fact that a free proton is very unstable, right? It decays into a proton and electron and an antineutrino. And there is one other pathway of the neutron decay, but that's when there is much energy available, right? This is when it's free and it has low energy availability, right? This antineutrino is an elementary particle, right? It's made of another 3 quarks, right? And it's an antiparticle of a neutrino, right? It's of neutral charge. Frankly speaking, I don't really remember much of what an antineutrino is other than this, right? And then you have these 3 representations. Z is your atomic number, N is a neutron number, A is the mass number, which is Z plus Z, right? This I won't be repeating again. This I'll be using frankly in all calculations, so you have to well remember it, right? Then coming to the size of the nucleus, which is pretty small, and you have the fact that the mass number is related to the radius of the nucleus by this formula, R equals R naught A power 1 by 3, right? Where R naught has this value, 110 power minus 15 meters. That's 1.2 formula, right? This value actually comes from, I think it comes from the Goldfoil experiment, I'm not really sure, right? And then this actually means that the density of nucleus is pretty much constant. It does not depend on the mass number, right? Because the density is mass, that's the mass number, divided by volume, which is radius cubed, right? And radius cubed is basically dependent on the mass number itself, right? That's actually a question. I'll do the workup again, but yeah. Then you have the mass energy and the nuclear binding energy equivalence. Mass energy, everybody knows the Einstein relation, E equals mc squared, right? And nuclear binding energy is basically something that arises from something called the mass effect, which is a phenomenon that occurs because the nuclear force is very, very strong, right? Inside the nucleus, what happens is when those small masses are basically condensed into such a small space, what happens is the potential energy actually increases drastically, and some of the mass of the protons and neutrons gets converted into something like something that holds these elementary particles stationary inside that very small space, right? That energy coming from this mass, right? That the mass that's lost to make up this energy is called the mass effect, and that's basically found by the mass of the protons plus the mass of the neutrons minus the mass of the whole atom itself, right? And you'll always notice that the mass that's actually found by experiment for any atom or for any atom is not exactly the same as the mass of the protons added to the mass of the neutrons making up the nucleus, right? There's something that you'll always notice, right? And by atom, I mean an ionized atom, a fully ionized atom. There are no electrons that we are considering actually, right? If you consider electrons that can and will throw off our calculations by a bit, right? Because a mass effect is pretty small. Uh, it's pretty small for the lower weight elements, right? And the binding energy is basically defined this way, right? I just highlighted the passage. I'm not reading it out. Right. And then here you come to binding energy per nucleon, which is a pretty good way to how to say this? Is a good way to separate your nuclei into 3 different zones, and is pretty much useful in finding out which elements can undergo fusion or fission to produce which other elements, right? These are 4 points that you have to be very careful in noticing, right? And you have to be you have to memorize them very properly, because these are very important, right? The binding energy per nucleon is practically constant between 30 and 70 because of some reason that's given below, right? You have many properties of the nuclear forces. You have many properties of fission and fusion here, right? And they determine what happens, where happens, where happens, right? Finally, from that, you figure out what a nuclear force is. The third and fourth fundamental forces of the universe. That's a weak and a strong nuclear force, right? Here we see the strong nuclear force. We don't really deal with the weak nuclear forces, but you see that there is these properties of the nuclear forces, right? This is also very important to remember, right? You have things about radioactivity, which was discovered by H. Becquerel in the year 1996. You have 3 types of radioactive decay. That's alpha, beta, and gamma, right? The alpha is where an alpha particle is emitted. That is 4He2 2 plus, right? It's not just 4He2. It's 4He2 2 plus, right? It's a helium nucleus. It's not exactly a helium atom, right? Beta decay, in which electrons or positrons, right? Depending on what it is, if it's electrons, then it's called the beta minus decay, beta minus for electrons. And if it's a positron, then it's a beta plus decay, right? A positron is B plus. And here, you may notice that positron is a new term, right? It's not introduced anywhere else. And positron is basically the antiparticle of an electron, right? If an electron and a positron meet, they annihilate each other and produce light or pure energy, right? And based on what type of decay it is, the mass number and the atomic number of the elements themselves, they change, right? There are actually radioactive equations, but we don't deal with them in this chapter. And then you have the final type of radioactive decay, that's gamma decay, in which high energy photons are emitted, right? They emit just photons. This is kind of a decay where you're basically, if you have some kind of an atom with some shell like this and a wider shell like this, excuse me, shell drawing, right? If this electron over here drops from this shell to this shell, it's going to emit energy outside, and that energy comes in the form of gamma, right? Gamma rays. This is basically what happens during gamma decay, right? Finally, you have nuclear energy, from which you start studying fission and nuclear fusion, right? It's basically theory. And you have controlled thermonuclear fusion, which may be important for some kind of a 3-mark or a 5-mark question that is asked in the NCERT board exams, right? So that's it for the chapter. Read through the summary, because the summary is actually good here. You have concise points about what happens where and what is important, right? But otherwise, I mean, if you want to go through this table, you can go through it, but the dimensional table is not really important here. And you don't really deal with the disintegration and half-life constant, so and whatever, right? Fine. Let's go to the exercises, right? Question number 1. Obtain the binding energy in mega electron volts of a nitrogen nucleus, given that the mass of the 14-10-7 nucleus is 14.1000307. Right? Give me a moment. Sorry for that. First things first, for all questions in physics, I'm just giving you a warning. Look at what is asked first, binding energy. Look at the units they've asked it in, mega electron volts, and look at what's given, right? 3 things you have to look at first, 3 things you have to be very careful in answer, right? The binding energy is EV, you are asked in MeV, and you're given that the mass of N14, I'm representing it this way, right? Don't get confused. Mass of M14 is 14.000307 units, right? This is what's given, right? You have the fact that the mass of the proton is 1.007825 U. Mass of proton is basically taken as a mass of hydrogen atom, right? Even though a hydrogen atom is proton plus electron, right? 1.007825 U. The mass of a neutron, small n, is 1.008665, right? This is one proton particle. This is one neutron particle. It's not one mole of particles, right? Be very careful in that also, right? So you have the fact that the addition of protons and neutrons, NPN, for nitrogen is basically 7 times the mass of proton plus mass of neutron, right? I'll actually denote this as P plus, right? Because I'm used to denoting my proton as P plus, not P. Right, it's basically 7 times this, which if you use the calculator or if you do addition, right, you get it as, I think it's 7 times 2 point double, is 2.01649, right, units, which is 14.11543, 543 units, right? That's the sum of the number of sum of the masses of protons and neutrons in the nitrogen nucleus. But since you are given that mass of 14N is 14.00307 U, we can basically calculate the mass effect delta M as MPN minus M14N. That is, I'm not writing the whole thing down, right? I'm just going directly with what is the answer. That's 0.11236, right? Units. That's the mass, right? Finally, the binding energy, if you had noticed the formula above, it's EB. Binding energy is equal to delta MC squared, right? Which is basically 0.11236 into 931.5 MeV, right? Because you have noticed that 1 U is 931.5 MeV per C squared. Since you have a C squared here, I'm just directly multiplying it by 931.5 to get a value in MeV, right? I'm just cancelling this C square with this C square, right? That's something that goes on in the background. I'm not explicitly doing it. So you have this result of 104.4 is the 4. It's 104.66334 megaelectron volts, right? That's your final answer for question number 1. Going to question number 2. Right. Binding energy of the nuclei 56, Fe26, and 209.83 bismuth in terms of in units of MeV. Right? You are asked for binding energy. You are asked in terms of megaelectron volts, and the nuclei given are 56 iron and 209 bismuth. Right? First of all, we'll go for iron. Right? The number of protons is basically the atomic number, that's 26. All right. The number of neutrons, on the other hand, is the mass number, that's 56, minus the number of protons, that is 30. Takes around, right? So you have the fact that MPN for Fe is basically 26 times 1.00785 U, 7825, plus 30 times 1.0086665 units. Okay. That is basically using calculator here. And kids, do not use a calculator because you won't have it in your board exams, you won't have it in JEE. Right? I feel like such a hypocrite saying that, but I have to say that. This is basically 56.4634, right? Since you are given that mass of 56 Fe is 55.934939, I'm just directly calculating the mass effect as this minus this, which gives me a value 0.528461. units. Do not forget the units, right? Just give me a moment to check. It's 40, 60, that's 100 over here, right? That's 54.95. Then, right, perfect. So finally, you have the fact that binding energy is basically delta mc squared. And by the same thing as above in the first question, I can basically write this as the mass effect 0.528461 in U into 931.5 MeV, right? This is basically 492.261 right? That's the binding energy. And if you want the binding energy per nucleon, right? This is just an extra step, but I'm just writing it down because there is no other question on binding energy per nucleon over here. Right. So if you want the binding energy per nucleon, that is energy of binding, that's 492.2614 divided by the number of nucleons, that is a mass number, that's 56. This is in megaelectron volts, right? This is 8.79 or 0383 megaelectron volts, right? That's the binding energy per nucleon for iron. Since we have finished iron, let's go to Bi, right? Bismuth, again, number of protons is, you can see it's 83. I don't know why this is given as B1. Alright, it's Bi. 83. The number of neutrons, on the other hand, is 209 minus 83. That's 126 for all those of you who do not know what is elementary subtraction, right? Should be none, but who knows, right? That's the given data. And of course, you have the mass of 209 bismuth given as 208.9803. Right? That doesn't matter right now because I'm not using it. Right? Let's find the mass of the protons and neutrons. That's 83 times the mass of proton plus 126 times the mass of a neutron. Right? I'm not writing the values down because it's not irritating. Right? Directly going with the value substitution, this gives me a value of 210.741265. 1265, right? This seems like 1,200. Right? Finally, you have the mass defect defined as NPN minus M of 209 decimal. That's basically 210 this minus 208 point this, which is 1.760877. That's your mass defect, right? And so you can easily find out the energy of binding. That's delta mc squared. By the same logic above is 1.760877 times 931.5 MeV, which is basically 1,640.256926. Wow. 926 MeV. Right? Finally, I've touched 1,500 MeV. This is a heavy atom, of course. Right? But if you see the energy of binding per nucleon, you'll notice that it is basically EV divided by 209, right? Which is, I'm not writing the value of EV because it's large, right? And I'm pretty excited about that. Which is basically 7.84 8119 megaelectrons, right? You'll notice that this is less than what you got for iron. That's because iron actually marks the maxima of the binding energy per nucleon curve. This is there in a previous page. I'm not exactly up to taking it out because I wanted to see the message. Right? That's it for the second question. Just give me a moment. Just a moment. Cool. Question number 3. Right? A given coin has a mass of 3 grams. Calculate the nuclear energy that will be required to separate all the neutrons and protons from each other. Assume that the coin is entirely made of copper 63 atoms. Right? First of all, you are given that the mass of 63 copper is 62.9 92960 unit, right? First thing. Second thing is mass of coin is 3 grams, right? Notice that one mole of copper atoms, right? 1 mole of 63 Cu has a mass of 63 grams, right? You don't deal with this actual mass over here when you deal with 1 mole. You basically convert the mass number into grams, right? So 3 grams of 63 copper, right, is 1 divided by 63 into 3 mole, right? Simple, because 1 mole is 63 grams, 1 gram is 1 by 63 moles, and 3 grams is 1 by 63 into 3. Right? That's 1 by 21 moles. With me so far. So we have the fact that this coin contains 1 by 21 moles of copper 63. Right? First thing. I'm not going to use this. I'm going to use this much further. This immediate step does not need this calculation actually. Right? For one atom of 63 Cu, right? We have to figure out the binding energy, because that is the energy required to separate all neutrons and protons, because that is the literal definition of binding energy, right? For this, we have the fact that MPN is basically number of protons, that is the atomic mass, number of copper into the mass of protons 1.007825 plus the number of neutrons, that is 34, into the mass of neutrons is 1.008665, right? Which is basically 63.521535. Give me a sec. It's 63.5215. Right. That's mass of protons and neutrons. Thus, the mass defect is basically this value minus this value, which is again using a calculator. I'm not writing the values down. It's 0.591935, right? And so you have the final fact that EV is basically delta MC squared, which is 0.591935 into 931.5 MeV, which is basically 551.387,453, right? This is the binding energy for one atom of copper 63, right? Remember this guy. Finally, to find out the net energy required is basically the number of atoms in 3 gram of copper into energy per atom, right? It's actually MeV per atom if you want to be very specific with the units, but nobody actually cares if you just leave this out. And you can just say it's MeV, right? So you have the fact that the final energy E required is basically EV times the number of moles times the Avogadro constant, right? Because this value gives us the number of atoms of copper, right? This value is the number of atoms, and this value is the energy per atom, right? That is basically I'll substitute EB at the last, right? It's into 1 by 21 into 6.023 into 10 power 23, right? This is actually I was just directly substituted there. It's like right? 521.387453 into 6.023 by 21 into 10 power 23, which is basically 158.143173 into 10 power 23 MeV, right? If you want to convert this into joules, is basically this value into 1.6 into 10 power minus 13, right? Because 1 electron volt is 1.6 into 10 power minus 19 joules. and mega is 10.6 basically, right? So that gives you a value of 253.029,076 into 10 power 10 in joules. Right. This joules is SI unit. I'm just basically writing this in joules because you're given a mass of 3 grams. Right? That's question number 3. Going to question number 4. Very simple question. You're given that the ratio of, you're asked the ratio of nuclear radii of gold isotope 197 AU and a silver isotope 107 AG. Right? So it's basically 197 AU and 107 AG. Right? And you know the fact that your nuclear radius R is equal to R naught A power 1 by 3. Right? So basically RAU divided by RAG. Since R naught is a constant, it gets cancelled out. I'm not writing it down. It's atomic mass of AU divided by atomic mass of AG under cube, right? This is basically cube root of 197 by 107, which is 1.256, right? 6 place of pressure because I think this chapter likes 6 place of pressure. That's it. Cool. That's question number 4. Question number 5. The Q value of a nuclear reaction is defined by this. Determine from the given data the Q value of the following reactions. State whether the reactions are XII or cool. So you're given this. I'm not writing this down again. Right? First reaction, that's hydrogen plus tritium giving 2 deuteriums. This can go the other way around also, but if it goes the other way around, that's actually called fusion, right? Yeah. So it's basically the Q value over here is something like let me write this value Ma plus Mb minus Mc minus Md as delta M, right? Is basically delta M C squared, right? Notice that this C squared is a positive constant, right? Whatever happens wherever you're in the universe is going to remain the same. C squared is positive, it's a constant, right? The only thing that differs is this delta M. So we just have to wait. You have to determine the Q value also, whatever. So just a note, if you're just asked whether the reactions are exo or endothermic, you can basically determine the mass value delta M and say if it's exo or endothermic. That's very easy. If this mass value is negative, it's exothermic. And if this delta M is positive, then it's endothermic. Right. Wait. I'm sorry. I said the opposite. Right. If this mass value is negative, then it's endothermic. Right. That means that energy needs to be supplied to the reaction to actually make it proceed. And if this mass value is positive, then it's exothermic. Right? You can say that basically Q is the amount of energy that is released from the reaction, from the nuclear reaction. Yeah. Right? So I'm just getting a bit. So for number 1, delta M is basically mass of 1H1 plus mass of 3H1 minus 2 times the mass of 2H1. Right? Mass of 1H plus mass of 3H minus 2 times mass of, right, which is, you can see from the given data here that it's first one is 1.007825 plus mass of 2H is 2.014102 minus, wait. I'm sorry. Mass of 3, that is 3.016049 minus 2 times 2.014102 unified units, right? That is basically minus 0.00433. That is mass. Just give me a sec. Yeah. So you have the fact that your Q value is basically delta M C squared. That is minus 0.00433U, right? 1 second. 433 into 931.5 MeV, which is basically minus 4.033, it's 0.33395 right? Since it's negative, this value since it's negative, you can basically say that the reaction is endothermic, right? I'm not writing the okay. You can say that the reaction is endothermic. And going to the second question, yes, sec. So for the second question, I'm directly going with delta M. That is 2 times, wait, what's happening? It's 2 times 12C, mass of 12C, minus mass of 20 neon, minus the mass of 4 helium, right? This is also a fusion reaction. Over here, mass of 12C is basically 12, so it's 24, minus the mass of 20 neon is 19.992439, right? And the mass of 4He2 is over here, that's 4.00263 units, right? And that gives you a value of 0.004958 units, right? I'll just draw 5 and 8 again. It's 0.004958 units, right? That's the change the mass. So your Q value is basically delta MC squared, that is 0.004958 into 931.5 electron volts. This is basically 4.618377 megaelectron volts, right? This is a point. Since this value is positive, this reaction is exothermic. That's how XII is done, right? Going to question number 6. Question number 6 is that we think of the fission of a 56 ion nucleus into 2 equal fragments of 28 aluminum, right? They're asking if the fission is energetically possible. The theory behind this is if your fission or fusion reaction is endothermic, then it is energetically not possible, right? I'm writing in a shorthand, just understand, right? If the reaction is exothermic, right? So if the reaction is exothermic, then the reaction is energetically possible, right? And this means that Q value is basically less than 0. This means that Q is greater than 0. Right? That's the theory behind this question. Right? And you are basically, you are since you are given that is a fission of 1 Fe 56 into 2 equal 28 Al nuclei. So you can basically write in the reaction as 56 Fe 26, giving rise to 28 Al 13 plus 28 Al 13. Right. This is your reaction. This means that delta M, as defined in question number 5, is basically 2 into 27.98191 minus 55.93494. Yes. Right, wait. I have to change the minus in the plus. Right. It's this mass minus this mass. It's not this mass minus this mass. Right. So it's minus 2 into 27.98191. So 9. Because this is what's on the right hand side. And this is on the left hand side is 55.93494. And the units is unit and mass units. This is basically, I'm not doing the explicit calculations. This is basically minus 0.02888 units, right? And from this, basically, you can say that Q value is less than 0, right? Because the sign of M or sign of delta M denotes what is Q. But if you want to calculate the Q value, that's also not a big deal. It's basically delta MC squared. And by the same logic as above, it's 0.02888 into 931.5 MeV, which is basically minus 26 0.90172 in, right? So Q is less than 0. This means that it is energetically not possible, right? So basically you can say that this by material, right? And basically say that this fission, this answer is no. Fine. Going to question number 7, right? Fission properties of 239 plutonium are very similar to that of 235 uranium. The average energy released fission is 180 MeV. And they're asking you how much energy is released if all atoms in 1 kilogram of pure plutonium undergo fission, right? For that we know that one atom of plutonium, right? One atom of 239 plutonium releases 180 MeV of energy, right? That means 1 mole of plutonium, because it's easier to work with moles when you're given things like kilograms, right? 1 mole of plutonium is going to basically release the Avogadro number, that is 6.023 into 10 power 23 times 180 into 1.6 into 10 power minus 13 joules, right? Because you're working with kilograms, it's also easier to work with joules. So this is basically, give me a second. Yeah. Okay, wait. I don't really need to calculate this out. But if you want to calculate this out, this will amount to, I think, this amounts to 1734.624 into 10 power 10 joules, right? And you have to note that 1 mole of 239 plutonium has a mass of 239 grams, right? Therefore, 1 kilogram of plutonium, right, or 239 plutonium, you have to mark the decimal points, right? So this is 1000 by 239 moles, right? That is 4.184 is 4.1841 moles, right? Since this is the energy per mole that's released, you have the fact that this releases an energy of 4.184 into 1734.624 into 10 power 10 joules. This is basically 7257.841 into 10 power 10 joules, right? Right. There will be a small error if you do this calculation directly, but what it is, I took this fraction and this value and totally multiplied it in a calculator, right? That gives me a pretty a more accurate answer. But if you say that the answer is 757.66 into 10 power 10, that's also fine. Nobody cares, right? That little amount of an error is perfectly acceptable, right? So yeah, I had to say that because that's a disclaimer, right? And this value basically condenses yeah. So this value is basically what you're looking for. In scientific, in standard form, it's basically 7.257841 into 10 power 13 joules, right? That's the standard form. Any one of these forms are accepted. Both are the same, right? And wait, since you're asked in MEV, that will basically convert this down to MEV. That's okay. Wait, I shouldn't have done this 1.6 here. Right? But yeah, converting this down to MEV is basically dividing this by 1.6 into 10 power minus 13, right? This divided by 1.6 into 10 power minus 13. So you have something like, wait, it's 7.257841 divided by 1.6. That's 4.53615, right? Approximately. It's approximately equal to 4.536151 into 10 power 26 MeV equals, yep, all right. So you've answered question number 7. Last 3 questions, right? Question number 8. How long can an electric lamp of 100 watts, power is 100 watts, kept glowing by fusion of 2 kilograms of deuterium? Mass of deuterium given is 2 kg, right? Note that 1 unit of reaction corresponds to 2 units of deuterium, right? 2 units of deuterium, D or 2H, whatever you want to call it, right? That releases 3.27 MeV. That's what's given here, right? 2 units of deuterium combined to give helium plus a neutron plus 3.27 MeV, right? This is a fusion reaction, of course, right? So if 1 unit of reaction is 2 units of D, this basically corresponds to 4 unified mass units of D, right? So 1 mole of reaction generates Na, Avogadro number, times 3.27 MeV of energy, right? This consumes 4 grams of deuterium. Cool. So basically the correspondence goes that 4 grams of deuterium releases this much amount of energy. Therefore, 2 kilograms of deuterium is 2000 by 4, that's 500 moles of reaction, right? 500 moles of reaction. Therefore, this basically releases an energy equal to 500 times 6.023 into 10 power 23 into 3.27 into 1.6 into 10 power minus 13 joules, right? Because you are given the power in watts, you need the energy released in joules, right? And so this is basically the net energy released, right? The energy released over the whole fusion period, right? You don't care how much time the fusion takes, you don't care how much time the fusion runs for. This care was the net energy, right? And so this is basically, is basically 156.168 into 10 power 10 joules, right? This is the net energy. Therefore, time it runs is basically net energy divided by the power, right, in seconds. This is basically 157.56168 seconds, right, into 10 power 10 seconds. So 1, right. This, if you convert it down to years, is basically divide by 3600, divide again by 24, divide again by 365, right? You don't consider leap years when you're going to convert seconds to years, because that anyway inherently contains an error, right? So you basically round this down to 49,962 years, right? A surprise calculation goes like this: 2 minutes, 2 hours, 2 days, and then 2 years, right? You have to divide by 60 for this. You divide again by 60 for this. You divide by 24 for this. And you divide by 365 for this, right? Finally, you get 49,962 years. That's how long you can run an electric lamp of 100 watts by fusion of 2 kilograms of deuterium. The only thing that stops you from doing this is getting this 2 kilograms of deuterium properly and carrying this out safe. Nothing else, right? Going to question number 9. Second last question. Calculate the height of the potential barrier for head-on collision of two neutrons, right? Two neutrons, consider them as Hart spheres, AB, right? Sphere center, everybody knows the concept of charge concentration at the center. It's plus 2e, it's plus 2e, right? And the radius is 2 centimeters, whatever, right? So the net distance between the two centers is 4 into 10 power minus 15 meters, right? It's 2 plus 2. Net charge is 2e plus 2e and 2e, right? And since it's a head-on collision, you basically consider that they just touch each other. There is no deformation, there's no elastic collision, there's no elastic property, nothing. Hart spheres colliding each other, when they're just touching, they're finding the potential, right? Potential V is given by for two point charges or for two spheres by kq squared divided by r. Everybody knows this, right? That's basically 9 and 10 power 9 into 4e squared, because it's 2e into 2e, that's 4e squared, divided by 4 into 10 power minus 15 meters, right? 4 cancels out, right? Expanding e squared, that's basically 9 into 10 power 26. I'm considering bringing minus 15 up, that's plus 15. 9 plus 15 is 20, is 24. What mass are so 24 into 2.56 into 10 power minus 33, right? Because 2.56 comes from the fact that E is basically 1.6 into 10 power minus 19 coulombs, right? This is in volts. This whole thing is in volts, right? This is basically 9 into 2.56. That's what? Wait a minute. It's 2 neutrons. Why am I considering it as 2? Just a single E. Just a single E. Really sorry for that. Really sorry for that. Neutron is 2H1, right? So it has 1 neutron and 1 proton here. It does not have two protons. It is not helium, right? I don't know why I considered it as helium. It's a plus E. It's another plus E. It's not plus 2E, right? You won't have this 4 anyway. So this 4 won't cancel out, right? There is still a by 4 over here. And 256 by basically 0.6, because 64 4s are 256. Cool. So you have this goes 10 power minus 14. It's 9 into 0.64. That's basically 6 9s are is 5.76 in 10 power minus 14 volts, right? Which you can convert to electron volts and say that it's basically 3.6 into 10 power 5 kilo electron volts. Wait, no. It's 610 power 5 electron volts, right? Because to convert volts to electron volts, you divide by 1.6 into 10 power minus 19. That gives you 3.6 into 10 power 5 electron volts. That's basically 360 keV. That's a potential barrier, right? Then, last question. From the relation R equals R naught A power 1 by 3, show that the nuclear matter density is nearly constant. Okay, right? This is what I meant by the proof I said earlier, right? When I said that the nuclear matter density or the nuclear mass density is nearly constant for every atomic mass number, right? And atomic number, of course, right? So first things first, note that the nucleus is a hard sphere, right? Which means that there is no elasticity, there is no dent, or there is no some kind of deformation over here. It's a hard sphere of radius r, mass A, right? You have to consider the nucleus is a hard sphere, because otherwise the formula the proof becomes nasty. Cool. And you have proof for it being approximately spherical, right? That means that the mass of the nucleus m nuc is equal to the mass number A. The volume of the nucleus V nuc is basically the volume of a sphere of radius r, that's 4 by 3 pi r, right? Therefore, the density rho is basically mass divided by the volume of the nucleus. This is basically A divided by 4 by 3 pi r cube. Since there is a 4 by 3 in the denominator, I'm bringing that 3 out to the numerator, right? I'm multiplying it, dividing by 3, basically. Right, it's 3A by 4 pi r cube, right? That's the first formula for density. That's what we can find by elementary substitution, right? Thing is, we are also given this relation that R equals R naught A power 1 by 3. Substituting that into this, R equals R naught A power 1 by 3. All right, you get rho equals 3A divided by 4 times pi times R naught cubed into A power 1 by 3, the whole cube. This is basically 3A divided by 4 pi into R naught cubed into A. A cancels out. This is 3 by 4 pi R naught cubed. right? This is the formula for density. I'm writing it down again. Sorry for that. Right? Rho is 3 by 4 pi r naught cube. Right? We all know that 3 is a constant numerical. 4 pi is a constant because both are numericals. R naught is also a constant that is equal to 1.2 into 10 power minus 15 meters. Right? So everybody knows this. Right? Because I said it earlier also. So you have the fact that everything here is constant. And so this value is also a constant, right? Because it's not dependent on any variable quantity. Therefore, we have proved that the nuclear matter density rho is constant, right? R is nearly constant, whatever, because R naught need not necessarily be the same for every value of, every value of every value of the atomic number. It changes a little bit based on the electron-proton repulsion attractions and the proton-proton repulsions. That also happens, right? So this R naught's value, even though it's given as 1.2 10 power minus 15, it varies a little bit, right? Very minutely, but it varies. So it's not exactly constant, but it's very nearly constant. So your nuclear matter density is very constant, right? That's proved, and that completes the exercise on the chapter nuclear, right? I'm gonna tell you, go through the summary, go through these parts of the fusion stars and why exactly that kind of a process does not cannot happen on Earth. Why exactly we haven't found anything, and what are the things that actually stop fusion from taking place, right? Those things are given here. Those things are important for boards, right? At the same time, read about fission. Take care of these. Take care of the chain fission reactions, right? And go through the graphs because the graphs are important, right? Thank you all.